We're now going to talk about standing waves of sound. And remember that all sound is a pressure wave, but it's a longitudinal wave. So because it's a longitudinal wave, we need to plot either displacement or pressure. And displacement is what we typically plotted. And remember that what we actually have is displacement in the direction of travel. So we don't really see a picture of what the wave actually looks like. We have to infer how the motion of the molecules of air can actually be plotted. We are also going to plot pressure, which is something I've mentioned before, but we haven't actually done yet. Now this is still sinusoidal. Again, we could be dealing with more complicated waves, but as I've said before, complicated sound waves are just sums of many different sinusoidal waves, so we're still going to just work with single sine waves. Our boundary conditions now are a little bit different. And how you can think about this is I have a wall, and this is going to be, say, part of a tube or a box, and we have some air molecules in it. And again, right now we're just thinking of these as basically billiard balls. And so if I have all of these billiard balls that are making up my air in this tube, some of them are really close to the wall and some of them are free to move. So these air molecules are really able to move back and forth however they are pushed by the wave. But these air molecules really can't move to the left. Now you might say, hey, well they could move to the right. But the problem with that, if you imagine how many air molecules there actually are in this tube rather than how much I've drawn, that if you consider all of the air molecules that are right against the wall and say, well, let's have them move to the right, that would actually create a vacuum between them and the wall, and that's not going to happen. So what we say is that our air molecules that are right against the wall do not move. Okay, so we say that the displacement is 0 of these, that these are all free to move, but the ones that are right up against the wall, they stay in place, that the wall isn't going to push them to the right, but they can't be pushed through the wall. So what that means is we're going to have displacement nodes at the wall, and that should remind you of what we talked about for strings. So even though the terminology is going to be different and the picture is different, at least initially, when we have a closed wall, we have a very similar boundary condition in that our displacement is 0. So let's think about what this looks like, and we're going to look at the m equals 2 mode. How do I know it's the m equals 2 mode? Well, there are 2 bumps. And remember, if this is a standing wave, we might frequently plot it by showing multiple moments in time, right? One where there's nothing, and so on. So again, you might normally see it this way. So we see that it's a standing wave, and we see that there are 2 bumps, so it's m equals 2. But what we're doing here is actually breaking it up into a few moments in time. We have our initial condition, we have a quarter of a cycle, and then we have half of a cycle. So our initial condition, remember that our wave, our displacement is going to be in that like x direction, right? So when we're thinking about delta x, that is motion from equilibrium, right? And then we can talk about it plotted as a function of position. So the longitudinal wave means we're plotting delta x against x. We're not plotting like delta y against x. So some of these molecules that were in the right have moved to the left. The molecules that were to the left have moved right. That's why you end up with more molecules in the middle. So what's helpful to compare is actually this middle condition here. So there's a moment in time where we have uniform pressure. So all of our molecules are effectively at equilibrium. Now you can say, wait, if this is what it looked like initially and then it was all gone, where did the wave come from again? This isn't to say that our velocity is 0 everywhere, that these molecules can be in motion at this point. They happen to be at equilibrium. And they're not all in motion per se, but the velocity depends on where they are. So don't make the mistake of assuming that these are stationary and in equilibrium. They're at equilibrium and many are moving. So in this situation, again, going back, you can see that there's less density here, which means some of these were to the left here, and some of these were on the right here. So again, this means some of these moved to the right. We have a positive delta x. This being negative means that some of these have moved to the left. Again, it's really helpful to understand how to go between a picture like this and one of these plots. So sometime later, we have them moving, And then what's happened is that there was a chunk of these effectively that started moving to the left. Here, they're back in equilibrium, but they're actually still moving to the left. So what happens is they basically overcrowd this area. We can imagine this group moving to the right. They now have reached equilibrium over here, but then they overcrowd this area. So again, at this point, we see that we have a net displacement to the left over here, that these molecules are to the left of equilibrium. These molecules are to the right at equilibrium. But there's some right in the middle that actually stay at equilibrium, right? So we still actually have a node here. But what a node of displacement means when we're talking about these longitudinal sound waves or pressure waves is that your air molecule is just sitting still. And again, we've said that it's happening at the very, very edge as well, right? So at the very edge, there's a couple hanging out, not moving at all. And that's still true, but the bulk of our air molecules are bouncing back and forth. So that's kind of a simple way to think through what's going on here. So again, this was the m equals 2 mode. We still have m equals 1, m equals 3, m equals 29, whatever you want. So that was displacement. Now let's talk about pressure. And I think that this picture isn't particularly helpful other than remembering you have a node of displacement there, a node of displacement there, a node of displacement there, as long as we are talking about m equals 2. If we want to talk about pressure equilibrium, remember that the equilibrium position of displacement delta x is just 0, being back at equilibrium. For pressure, what does this 0 line represent? It doesn't represent 0 pressure. That doesn't make sense if we're talking about an enclosed gas. This is atmospheric pressure. So there's some equilibrium pressure that we can have higher pressure than or lower pressure than. So when we say that the equilibrium pressure, we just mean what is the pressure that corresponds to basically that 0 line. Now then the next thing that's interesting to look at is how the nodes of pressure correspond to the antinodes of displacement. And I think this is pretty tricky to think through. So we have this special point here in the center, which corresponded to these atoms or molecules not moving. But notice that here, that's actually your antinode of pressure. So that means that we have the biggest oscillations in pressure there. And the reason for that is if you look right now, this would be equilibrium. But remember, if I go back up briefly, if I go back up to the previous slide, we saw that in the center here, you had the biggest compression when they all came together, and then you had the rarefaction, basically the lowest pressure when they all pulled away. So effectively, when you have a point that is your node in displacement, that is the point that your molecules are all piling up against in both directions, causing the highest pressure, versus pulling away from in both directions, causing the lowest pressure. So that's conceptually the reason why we get this antinode here that corresponds to the node in displacement. But I think that is tricky to think about, and I really encourage you to spend some time making sure that that makes sense for you. Now, vice versa, there's going to be a certain point where we have antinodes of displacement. So these, for instance, are moving kind of the most to the left and the most to the right. That's actually your node of pressure. That at this point in the tube, you're pretty much at atmospheric pressure. Nothing is pushing together here. You're kind of pushing through to the left or through to the right, but this area always stays at atmospheric pressure. So again, the most helpful way to think through this is that your antinodes correspond to your nodes and vice versa. Another thing you can do is think about displacement always being your sine curve and pressure being your cosine curve. Now notice that this is true for closed tubes. What is coming in the next video are tubes with openings. So what I'm saying here about sine and cosine isn't always true. This is only for closed tubes. So be a little bit careful about that. The logic that antinodes correspond to nodes, that is always true. So the last thing to notice here that again might simplify this a little bit is that whether we're looking at displacement or pressure, our wavelength and frequency are the same. So if I take my wavelength, which is in this case my whole length, if you look down, it might look like a different wave, but remember that wavelength can be something like this, but we've also talked about wavelength being the distance from peak to peak. And notice that we have a peak here, but now be careful and remember that it goes down and then up. So we have another peak here. So this is still a measure of our wavelength. So we have the exact same wavelength, and since these are both waves in air, they have the same wave speed, which means they have the same wave frequency. So whichever way we represent or talk about our waves in terms of displacement or pressure, we still have the same wave speed, frequency, and wavelength. It's just really a question of which one you're plotting.